So hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Thomas is going to talk about the strong cospectralities in trees.
Okay, so thank you for the invitation. So today I will talk about strong cospectrality in trees, and everything here is joint work with Emmanuel Juliano and Gabriel Coutinho. So let me begin by talking about perfect state transfer. That gives the motivation for strong cospectrality. So given a graph G with adjacency matrix A, we can consider the exponential e to the ita, and we say that there is perfect state transfer between the vertices I and j at time tau if e to the I tau a, the entry ij of this matrix, as modulus equal to 1. So this is perfect state transfer. And we say that there is pretty good state transfer between I and j if for every epsilon bigger than 0, there is some time tau such that this entry is at least 1 minus epsilon. So if we have the spectral decomposition of A written in this way, sum theta r er, then we can write the exponential e to the ita in this form. So if we look at this entry, we can see that this entry has modulus equals to 1. Then we have this equality, and using this equality, we can obtain that if there is perfect state transfer between I and j, then all these entries in these projectors are equal. But here you have a plus minus sign for the entry ij. So if we have PST between I and j, then we have these equalities for each of the projectors in the spectral decomposition of A. And this is also true for pretty good state transfer. So both PST and PGST imply the series of equalities. So this motivates the definition of strong cospectrality. So given a graph G with adjacency matrix A and the spectral decomposition of A written in this way, we say that vertices I and J are strongly cospectral if we have these equalities for the projectors in the spectral decomposition. Strong cospectrality is a more refined notion of cospectrality because cospectrality is equivalent to this first equality in these two equalities, right? Yes. So we can obtain from this that PST or PGST between two vertices I and j can be characterized by these vertices being strongly cospectral, plus some extra conditions on the eigenvalues and eigenvectors of the adjacency matrix. So in particular, using this equivalence, one can prove that PST can be decided in polynomial time with respect to the size of the graph. This was proved by Gabriel and Chris. And the same is true for PGST, but there is only a finite time algorithm. Okay, so let me talk about cospectral vertices. So as I said before, two vertices I and j, they are cospectral if these entries in the projectors are the same for each projector. And this is equivalent to the assertion that all the entries in these powers of the adjacency matrix are equal, or in other words, that the number of closed walks beginning at the vertex I of length k is equal to the same counting for the vertex j, or written in terms of generating functions. We have this equality here in the middle, and the walk generating function can be written in terms of the characteristic polynomials of the graphs. So this equality right here is in fact equivalent to this equality of characteristic polynomials. So vertices I and j are cospectral if and only if the characteristic polynomial of the graph G minus I is equal to the characteristic polynomial of the graph G minus J. So in particular, vertices I and j are cospectral if the graphs G minus I and G minus J are isomorphic. For example, in this graph right here, these vertices in green are cospectral because when we remove these vertices, the graphs that we obtain are similar. And also because of this fact, all the vertices in a vertex transitive graph are pairwise cospectral. So for example, for the complete graph or for the Peterson graph. But for strong cospectrality, things are different. So already in 2017, Goetzel and Smith proved that if two vertices I and j are strongly cospectral, and there is an automorphism that fixes one of these vertices, let's say I, then it must also fix the other vertex j. So in particular, this result proves that no pair of vertices of Kn, the complete graph on n vertices for n bigger than or equal to 3 is no pair of vertices is strongly cospectral. So very different from cospectrality. And for perfect state transfer, it is already an observation from Kai in 2011 that if there is perfect state transfer from I to J and from I to K, then J equals K. So there is monogonimity in perfect state transfer. So this motivates the question if there is a graph with a large set of pairwise strongly cospectral vertices, right? So yes, these graphs exist. So in order to prove this, there is this theorem by Goetzel and Smith that says that two vertices I and j are strongly cospectral if and only if these conditions with respect to the characteristic polynomials holds. So this equality that characteristic polynomial of g minus I is equal to characteristic polynomial of g minus j. So I and j must be cospectral, and that this quotient characteristic polynomial of g minus ij divided by the characteristic polynomial of g has simple poles. So strong cospectrality is equivalent to this. So as a corollary, if the graph G has simple spectrum, then this rational function necessarily has simple poles by interlacing. So in the case that G has simple spectrum, strong cospectrality is in fact equivalent to cospectrality. So if we want to build a graph with large sets of pairwise strongly cospectral vertices, we can simply build a graph with large sets of pairwise cospectral vertices with simple spectrum. So in fact, this can be done using path products. So we can consider path products choosing A1 to AK in such a way that this path product has simple spectrum, and it obviously has large set of pairwise cospectral vertices. So for some choices of A1 to AK, we can obtain large sets of strongly cospectral vertices. And what about vertex transitive graphs? So for vertex transitive graphs, there is a construction by Sophia and Chris that there exists infinite families of Cayley graphs with a set of 4 pairwise strongly cospectral vertices. But for sets of size more than 4, the question if there is any vertex transitive graph with strongly cospectral sets is open. So Okay, so this is for graphs in general and for vertex transitive graphs. So what about trees? So why bother with these questions for trees? So there is interest in perfect state transfer in trees because trees model quantum systems which are likely cheaper and easier to build. But there is a conjecture by Coutinho and Liu from 2014 that no tree except for P2 and P3 admits perfect state transfer. And okay, so this is PST in trees. And what about cospectrality in trees? So it's easy to build large sets of pairwise cospectral vertices in trees. For example, we can take, if we take a star, then these vertices of degree 1 in the star, they are all pairwise cospectral. In fact, there is lots of trees with cospectral vertices that are not similar. So if we want, again, if we want to build large sets of pairwise strongly cospectral vertices in trees, it is better if these vertices are not similar because there is this condition that if an automorphism fixes one vertex, it must also fix the other vertices. So for example, here we have Schwenk's tree, which is the smallest tree with two cospectral vertices that are not similar. And more generally, there is a theorem by Jung from 2019 that for every k bigger than 2, almost every tree has k pairwise cospectral vertices that are not similar. So in fact, there is a very robust construction of large sets of cospectral vertices in trees, and we can guarantee that this construction does not have vertices that are similar to each other. And moreover, there are some constructions of strongly cospectral pairs that work well for graphs in general and in particular for trees. So for example, there is this construction by Gottsel and Smith from 2017 that these vertices I and j, we take any two vertices I and j in these graphs gi and gj, and we connect them by a path. And with this construction, if this condition is satisfied, that these quotients of characteristic polynomials are equal, then the vertices I and j are strongly cospectral. So using this construction is actually easy to build strongly cospectral pairs in trees. And there is this another construction by Gottsel and Smith from 2017 that if we take any graph H and some vertex K, and we consider two vertices I and j that are twins of degree 1 connected to this vertex K, then these vertices I and j, they are strongly cospectral if and only if this condition is satisfied. So this condition is equivalent to the fact that this vertex K, the eigenvalue 0 in H is in the support of K. So there are these two constructions, and using these constructions, it is easy to build strongly cospectral pairs in trees. And moreover, we can also construct large sets of pairwise cospectral vertices where strongly cospectral vertices come in pairs. So for example, for this graph on the left, the 4 vertices of degree 1, they are cospectral, and each pair on the left and on the right is a strongly cospectral pair of vertices. So on the left and on the right, they are strongly cospectral pairs, but vertices on the left are not strongly cospectral to the vertices on the right. So, and for this other graph, it's the same story. So all these vertices in green, they are cospectral, and each of these pairs is a pair of strongly cospectral vertices, and we can build larger and larger graphs in this way. So we can in fact build trees with, and in fact this construction can be modified so that these vertices are not similar. we can put graphs in each of these vertices in such a way that they are not similar to each other. So in fact, we can construct large sets of pairwise cospectral vertices in trees such that every vertex has some strongly cospectral pair. But if we consider the whole set, then the vertices are not strongly cospectral, all of them, with each other. So this motivates the question by Gutsu and Smith. If there is a tree with 3 pairwise strongly cospectral vertices, yeah. So and recently, in joint work with Gabriel and Emmanuel, we proved that there is no tree with 3 pairwise strongly cospectral vertices. So in fact, given these previous examples, we need to prove that we need to use the condition that the 3 pairs of the 3 vertices are pairwise strongly cospectral and not simply cospectral. So, as a corollary of this theorem, if a tree has 3 pairwise cospectral vertices, then its spectrum is not simple, because by a previous result, if a graph has simple spectrum, then strong cospectrality is equivalent to cospectrality. So in particular, in order for 3 pairwise cospectral vertices and in a tree to not be strongly cospectral, the spectrum cannot be simple. So, and more generally, the proof actually gives that if a tree has k pairwise cospectral vertices, then it has at most this number of distinct eigenvalues. All right. So I will open a notebook. Let me stop sharing so I can show some other things about the proof. So are you seeing the notebook?
Yes, we can see it.
Okay. Yeah, so we have this theorem by Jung, Coutinho, and myself that no that there is no tree with 3 pairwise strongly cospectral vertices. So let me say a few things about the proof. So the proof actually involves only the quotient of characteristic polynomials. So we are using only that this result by Gutsu and Smith from 2017 that I and J are strongly cospectral if and only if these conditions on the characteristic polynomial hold. So they must be co-spectral. So the characteristic polynomial of G minus I is equal to the characteristic polynomial of G minus J. And this rational function phi G minus I has simple poles. So since for trees, the characteristic polynomial is equal to the matching polynomial, the same is true for the matching polynomial in the case of trees. So there are no there is no pair of three vertices such that this condition holds for the matching polynomial in place of the characteristic polynomial. So for matching polynomials, this is interesting because there are some results about simple zeros for the matching polynomial. So for the matching polynomial, we can define this analogous notion of strong cospectrality using this condition right here. So in fact, for the matching polynomial, the same kind of proof gives that a graph in this way let's say that in a graph of this form, where there is this vertex V in the middle and I, J, and K are co-spectral, actually, this is what we prove for the characteristic polynomial. If we have a graph in this way and these vertices are co-spectral, then they cannot be strongly co-spectral. So this implies that I, J, and K cannot be all strongly co-spectral. And in particular, this graph G does not have simple spectrum. Yeah, so this is the main result we prove. So our proof uses only this condition about the characteristic polynomial that characterizing strong cospectrality in this way. And if we define strong cospectrality for the matching polynomial in this way, so two vertices are strongly matching cospectral if these matching polynomials are the same and this quotient with the matching polynomial has simple poles, then this result also holds for this other notion of strongly matching cospectral. And for the matching polynomial, it is interesting that there are some classes of graphs such that the matching polynomial has simple zeros. So, for example, if G is vertex transitive, or Hamiltonian, there is a Hamiltonian path, or claw-free, then the matching polynomial has distinct zeros. So this is interesting for the matching polynomial because these classes of graphs, these three types of graphs, vertex transitive with Hamiltonian path and claw-free, in these cases, the matching polynomial of these graphs has distinct zeros. And in this case, above, the matching polynomial does not have simple zeros. So, of course, these three classes of graphs are distinct from this class of graphs written above. And it's interesting that the same kind of tool used to prove this theorem about the zeros of the matching polynomial being distinct is actually used to prove that graphs of this type above have both zeros of the matching polynomial and of the characteristic polynomial. The zeros are not all distinct. So it's the same kind of tool used to prove this theorem for characteristic and matching polynomials above, and this theorem below for the matching polynomial. So it's this theorem right here that implies that a tree cannot have three pairwise strongly cospectral vertices. So why does it imply? Well, we only need to show that three vertices in a tree cannot all be in a path. So if they are not, if they were all in a path, we just need to verify that they could not be strongly cospectral. So in particular, if we prove that they are not cospectral, then using this result above, the theorem follows that no tree contains three pairwise strongly cospectral vertices. So why these three vertices in a tree T, they are not cospectral? We can see this simply by removing each of these vertices I, J, and K, and looking at the spectrum of the resulting tree. So if they were cospectral, we would have phi of T minus I equals phi of T minus J equals phi of T minus K. And in order to show that this does not hold, we simply remove the vertex J. So if we say that this tree right here is Ti, this tree is Tk, and this tree is Tj, then the largest zero of phi T minus J is actually the maximum. Let's say I denote by θ1, the largest zero of the respective characteristic polynomial of the graph. So so θ1 of T minus J is actually this maximum. So θ1 of Ti, θ1 of Tj, θ1 of Tk. And for the other vertices, I and J, so theta 1 t minus I is at least it's bigger than theta 1 of tj and theta 1 of tk, because the graph obtained by tj connected to this vertex j is a subgraph of this graph t minus I. So this is strictly larger to this maximum. One of tj, theta 1 of tk, and the analogous thing for this vertex k. So and using these facts is we can see that at least one of these, theta 1 t minus I or theta 1 t minus k, is larger than theta 1 t minus j. So that this equality cannot occur if the vertices I, j, and k are in a path. So using this theorem that these vertices in this way cannot be co-spectral, and this result above, it will follow that a tree cannot have three pairwise strongly cospectral vertices. So it remains to verify this theorem right here. So I will not enter the details of the proof. I will only give the punchline. So let's say we have a graph in this way above. So let's say we have a graph with I, j, and k, and some cut vertex right here, connecting these components of I, j, and k. So we want to prove that I, j, and k are not pairwise strongly cospectral. So what we actually do in the proof is that we write everything in terms of quotients of characteristic polynomials. So if we denote by alpha ig, this quotient right here, and similarly for j and k, then we can write strong cospectrality in the following way. So then we can write I and j are strongly cospectral if and only if alpha ig is all equal to alpha jg, and alpha ig theta, which is equal because of this equality above to alpha jg theta, is different from 0 whenever these quotients in the subgraphs are equal to 0. Or okay, so we can write strong cospectrality in this way using these quotients. And so the proof is by contradiction. If we assume that they are pairwise strongly cospectral, we can manipulate this kind of quotients using these alphas and show that actually whenever an alpha of this form is equal to 0, for example, if you remove V and look at this quotient, whenever this is equal to 0, then for the other vertices, if we assume strong cospectrality between I, J, and K, then we have this equality right here, alpha J, G minus V theta. These are both equal. They are equal because of cospectrality. And are not equal to 0. So we can reason using the strong cospectrality and prove this result right here, that this holds for every theta, that this condition right here is satisfied, and this holds. So why this implies that they cannot be strongly cospectral? Because if we look at the graph of these functions alpha, the graph is something like this. So the graph is asymptotic to x. When you go to minus infinity, then it has some poles. And in each branch, these alphas are continuous. So this is for all these alphas. So alpha I, the shape of these graphs is always the same. So alpha I, G minus V, theta for every theta. So if we look at the large negative time, so for large negative time, theta go into minus infinity, all these alphas, they are asymptotic to theta. So so for large negative times, in particular, they are all negative. So for every theta, all these alphas are negative. And similarly, when we go for theta very large, all these alphas are approximately theta. So for theta positive, these are all, in particular, they are all positive. All right, and this condition right here says that when one of them is equal to 0, the other ones, they are equal and they cannot be also 0. So we can, so to see that this is impossible, we can consider the following game. So consider we have some person right here, 3 persons on one side of a river, denoting these alphas. So alpha I, G minus V, alpha J, G minus V, alpha K, and that is a river right here. And we want these alphas to cross. So for large negative times, they are all on some side. And for large positive times, they are all on the other side. So we want all these persons to go to the other side of the river, and they can use a portal. So if they want to come back to this side, so this portal only goes in this way, because these alphas, they are all increasing, so they can go from positive to negative when theta increases, but not from negative to positive going through a pole. So so we want these three persons to cross this river, the three of them, in such a way that whenever someone crosses, the other ones cannot cross simultaneously and must be holding hands while one of them is crossing. And they can use this portal if they want to come back. So I left this as an exercise to see that it is impossible to do this. So since this is impossible, these vertices I, j, and k cannot be strongly cospectral in a graph of this shape right here. That's it.